Welcome to The Explainer. Today, we're going to dig into a paradox that you probably felt, even if you couldn't put your finger on it. Our computer chips, they haven't actually gotten faster in years. But somehow, the phone in your hand is a complete powerhouse. So how is that possible?
Well, let's get into it.
Okay, so let's start with a puzzle. For decades, we all just kind of expected computers to get exponentially faster, year after year. But if you look at the clock speed, that gigahertz number on the box, it just flatlined more than a decade ago. So what gives? You see, for a really long time, software developers got what everyone in the industry called a free lunch. They could just sit back, wait a year or two, and their exact same code would magically run twice as fast on the new hardware. And it was all thanks to this famous observation called Moore's Law. But here's the thing almost everyone gets wrong about Moore's Law. It was never really about speed. It was about density. It was about our incredible ability to cram more and more tiny transistors onto a single chip. Now, for a while, more density also meant more speed. But that perfect relationship, well, it was about to come to a screeching halt. And the reason why? We slammed headfirst into what engineers call the power wall. See, trying to make chips faster was generating so much heat that they were literally at risk of melting themselves. And at the same time, the transistors got so ridiculously small that electrons started to just misbehave, quantum tunneling right through barriers where they weren't supposed to go. The free lunch was officially over. So the entire industry needed a new game plan. If they couldn't make a single core faster, they thought, well, why not just use many cores working together? And this led to a massive pivot towards something called parallelism, a whole new strategy that relies on two very different kinds of processors, the CPU and the GPU. Think of it this way, all right? A CPU is like having a few absolutely brilliant chefs. They can cook any complex, gourmet dish you throw at them, one at a time. A GPU, on the other hand, is like a massive army of line cooks on an assembly line. Each one just does one simple task, like chopping an onion, but thousands of them do it all at the exact same time. One is built for speed on complex tasks, the other is all about massive parallel throughput. And if you look at how they're built, this whole philosophy makes perfect sense. The CPU uses up its precious space for big, fast caches and fancy control logic to make those single tasks just fly. The GPU, it scraps all that. Instead, it just packs in thousands and thousands of simple little math engines called ALUs. That's the raw muscle for doing tons of calculations in parallel. Now, the CPUs weren't left totally in the dust. They learned a pretty clever new trick to compete in this new parallel world. It's called hyperthreading, and it's this really slick way to make one physical core pretend it's actually two. So here's the magic behind it. A lot of the time, parts of a CPU core are just sitting there, idle, waiting for data to arrive. Hyperthreading is smart. It duplicates just a few essential bits, like the registers, which lets a second task jump in and use those parts that would otherwise be doing nothing. It's all about keeping that core 100% busy all the time. And the result of this? It's pretty amazing. This clever trick can squeeze out up to a 30% performance boost on the right kinds of jobs. That's a huge win for what's a pretty small cost in terms of chip design. Okay, but having thousands of cores is only half the battle, right? I mean, they're totally useless if they can't get the data they need to work on. And this brings us to the next massive challenge, memory. How do all these cores talk to each other and get information without stepping on each other's toes? So there are basically two main philosophies here. First, you have shared memory. Think of it like a team of people all working on one giant whiteboard. Everybody can see it, everybody can change it. The other way is distributed memory. This is more like each person having their own private notebook. If you want to share something, you have to explicitly write a note and pass it to someone else. And even inside that shared whiteboard model, things can get a little more complicated. Your laptop, for instance, probably has what's called Uniform Memory Access, or UMA. That means every core gets to the memory at the exact same speed. But in giant data center servers, they often use NUMA, where a core can access its own local memory way faster than memory that's on the other side of the board. It's really all about how good your seat is at the table. Okay, so the solution seems simple then, doesn't it? Just keep adding more cores and things will keep getting faster forever. Well, not so fast. It turns out there are some pretty fundamental laws of physics and logic that put a hard limit on how much speed you can actually get from going parallel. First up, we have the voice of pessimism. It's called Amdahl's law, and it states a really simple, kind of brutal truth. Any part of your task that absolutely has to be done in sequence, one step after another, will always be your bottleneck. It's the part that holds everything else up. My favorite way to think about this is the house painting analogy. You can go out and hire 100 painters to work on all the walls at the same time, that's the parallel part, but the entire project has to wait for that one person who's doing the prep work that has to be done in order. Buying the paint, laying down the tarps, taping the windows. You can't parallelize that. And the math here is just harsh. Let's say your program is 95% parallel. That sounds great, right? But that last 5% that has to run sequentially creates a hard ceiling. You can never make that program more than 20 times faster. I don't care if you have 1,000,000 cores. This sounds pretty bleak, doesn't it? I mean, if Amdahl's law is the final word, then what is the point of building these gigantic supercomputers with hundreds of thousands of cores? Are we just hitting another wall? Is it all just pointless? But then comes the optimist's rebuttal. It's called Gustafson's law, and it completely reframes the problem. It argues that, hey, when we get more computing power, we don't just solve the same old problems faster. No, we tackle bigger, more complex problems than we ever could before. And here is the key insight. As that overall problem gets bigger and bigger, say a much higher resolution weather simulation, that fixed sequential part becomes a smaller and smaller fraction of the total work. It becomes like a tiny drop in a huge ocean. The parallel work totally dominates, and suddenly those massive speedups are possible again. So, with these two competing laws in mind, how do we actually know if a parallel system is successful? How do we keep score? Because it's not just about raw speed, it's about being smart and efficient with all that power. We really look at three main things. First, there's speed up. That's the easy one. How much faster did we get? Then there's efficiency. Are our processor cores actually doing useful work, or are they just sitting around waiting for messages? And finally, scalability. This is the big one. It asks, can we keep that high efficiency as we add more and more processors to tackle even bigger problems? You know, the dream, the holy grail, is what we call linear speedup. 100 cores gives you 100 times the performance. But in the real world, the overhead of all that communication means your actual speedup is always going to be a little less. Your efficiency is never quite 100%. The whole game is just to get as close to that ideal line as humanly possible. So there you have it, the pivot from just trying to make one core faster to using thousands of cores in parallel is the real reason our computers keep getting more powerful. The true innovation wasn't about raw speed. It was about a total change in architectural thinking. Parallelism solved the power wall, but it leaves us with one final, massive question. What new architecture, what new way of thinking is going to solve the next great computing bottleneck?